G'day, this is my little test rig. I'm going to try and replicate forces on a bridge. On this truss bridge you can see here, it's a simple wooden one. I've clamped it, but the right side, as you can see over here, is on a bolt. So that is free to rotate, but it can't move left and right. This left side is my simulation of a roller. So it can slide left and right, but it can only provide vertical forces. In my case here, I've got a set of scales, and I'm going to try and measure the vertical force. Okay, so in reality we're measuring a down force, but because every reaction has an equal and opposite, if it's 100 newtons acting down and it's not moving, it's 100 newtons acting up. Okay, so does that make sense? It's fixed on that side by this bolt, and I'm gonna do two forces on it. One of them I'm going to push level with the deck, which will create or not create a force on the scales. So whatever you think it will do. And then I'm going to do another one where I'm going to pull on the top of the bridge and try and record with a known load. So this is just so I can measure how much I'm pulling on it. And I'm going to try and pull with kilo of force, which is 10 newtons, and I'm going to try and measure here the reaction force. Okay, so if I push on the bridge, or in my case, pull on it, because I can push here, or I can pull on the same spot. That's the rule of transmissibility. If I push right there, it's exactly the same as a pull force there, and it's exactly the same here. If I push up the top and I pull here, there's no difference whether there's a push or a pull. Okay, so in our case here, if I pull on the deck, if I pull dead straight, there should be pretty much zero force on the scales, if that makes sense. Because the force is through the deck, and moment is force times distance. So if it's got zero distance, the moment is zero. Because even if I put 100 newtons and it's got no distance away, the moment is zero. So force times distance. So if the distance has a number, for instance, if I pull on the top of the deck, top of the bridge here, and I measure how far away it is from down on the deck here. In our case, it's about that far. So it's got force times perpendicular distance. Okay. The only little tricky bit here is because my pin joint is below the deck, I would take it from the distance from the pin joint to the top. In every other example we're doing, in all the examples that you see in textbook, they take it from the deck to this point here because they put the pin joint in the drawings at that point. Okay, so I've actually measured from the bolt to the top, and it's 210 millimeters. Does that make sense? 210 millimeters from the center of the bolt to the very top of this bridge. Okay, so I'm going to pull on the top of the bridge with a kilogram of force, and because gravity is 10 or 9.8, I'm going to say it's 10 newtons. So I'm going to pull on this. I've zeroed my scales. It's pretty much zero. If you can see that. I don't know if you can see on here. Zero. I'm going to pull on the top of this bridge with 10 newtons of force. The scales should say 350. I'm seeing 330, 340, somewhere between 330 and 350 grams. Because these are scales, they're not measuring newtons. So if that's grams and I times it by 10, that's 3.4 newtons. And here's my calculation. Let me bring it up to the screen. Okay, here's my bridge. Okay, it's 610 millimeters from the left to the right, which is the same as 610 from that bolt to here. Okay, that's 610. I took it from the edge of the wood. lost me on that. At 610 millimeters. Okay, here's our drawing. I've got 610 millimeters from the left to the right. The right side has a bolt. The left side is a roller joint, and I my roller joint in a book would look like that. Okay, we know that, and the side's pinned. Okay, roller joint can go left and right, but it can only react vertically. Okay, I just measured about 300, let's say 330, let's say 340. Pretty generous. Okay, so I've got 10 newtons acting at top, 10 acting to the left. That was me pulling on it. The top of the bridge is 210 millimeters from there to here. Okay, so it is fourth times the distance, which is 10 times 210 millimeters, which is 2,100. Okay, that's going in, say, an anti-clockwise direction, so I'll give that negative. And the reaction here is going in a positive or a clockwise direction around the right side of 610 millimeters, 610 times RL, and this is my RL. Okay, I'm trying to work out what it is. So if I've got 210 times 10, 2,100, and that's negative and this is positive, so this is going to equal that one. So 210 divided by 2,100 divided by 610 is 3.4. 3.4 newtons is divided by 10 is 0.344 kilograms, which is 344 grams. So I was measuring somewhere between 330 and 350, which I think is pretty good. Last measure, that is measuring somewhere between, fluctuates because I can't hold my finger on it exactly, a little bit less than 340 often. I account for that loss, friction, millimeters of inaccuracy in my measuring, because I want to have nice round numbers, and also possibly my zero in here. I'm 3 grams out, there's a bit of a breeze blowing, but I'd probably include a lot of the losses in this joint as that rotates. If that's not 100% efficient, there's friction, so I'm going to lose some of my force in that bolt. Hopefully that makes sense. Yeah, that wraps up another hopefully helpful tutorial.